Okay, so it's meant to be a pretty basic introduction. I'm not planning on covering that much material, so please feel free to interrupt so that it's as pedagogical as possible. And I don't really have a punchline, so I can stop pretty much at any point. But so what I want to talk about is I want to introduce a framework that has been developed over the past, well, it's a bit older, but there were like some recent developments in the past 3-4 years to kind of construct lattice models that have non-invertible symmetries and manipulate the symmetries in these lattice models. And what is nice about the working on the lattice is that you can establish a nice dictionary between the category theory and basically the physics. Almost every category theoretic statement you can think of, we have a nice lattice equivalent, and this framework is basically establishing this dictionary to some extent. So I will be focusing on finite symmetry, 1 plus 1D. And as most of you know, the mathematical framework I'm going to use to describe these finite symmetries are fusion categories. And here the idea is to think of the fusion category as essentially encoding the properties of the topological defects so with the idea that we define the symmetry as basically having a collection of topological defects you can couple to your theory. So it's topological defects, so they have, in the context I'm going to talk about, they can have two sort of physical incarnations. Either they correspond to twists that you can use to define twisted hyperspaces, or they are just symmetry operators. And so it's a category in particular because these are, so the idea is that these are line operators. You can have junctions between the corresponding line operators, which are topological, which correspond to the objects and the morphism of this fusion category. So the framework I'm going to present works for an arbitrary fusion category, but it's nice to specialize to the case of non-anomalous symmetries. I can clarify later why I refer to those as non-anomalous, but these are the ones which are obtained as category of modules over some half algebra. The general case requiring weak half algebras instead. And so for example, we just do 2 examples. If you take the category of modules over the group algebra, so when I use like square brackets here, I use the group algebra. I mean the multiplication of this algebra is given by the multiplication of the group itself. This is just equivalent to the category of representations, with the maps being the G-equivariant linear maps. And another nice example, which is its dual in various ways, is to take instead the algebra of functions on the group with pointwise multiplications. And this is equivalent to the category of G-graded vector spaces. And actually, since I'm going to use it implicitly later on, it's also nice to notice that this category is also equivalent to the category of comodules over the group algebra. And so here in particular, these 2 half algebras are dual as half algebras, which will play a role later. So I'm going to focus actually mostly on these 2 examples because, well, so VecG is basically just the ordinary G symmetry. So let me maybe just clarify if you're not familiar with this. So a graded vector space is just a vector space. It has a grading by the group, and so the maps are grading preserving, and the tensor product is given by the convolution product as follows. So this is just the fusion category version of when we have an ordinary symmetry. And this example, it's nice because it's a very simple case of a non-invertible symmetry. So I'm mostly going to focus on these 2, but the framework I'm going to use, I mean, not just the framework, but like the derivations, like really generalized to the case of modules over half algebra. And then the framework also works for the more general case with a couple of caveats, but everything is under control. Okay. Well, in that case, it will be, but actually we could also do non-unitary. We've done some examples already with like non-semi-simple tensor categories. You lose the unitarity at the end of the model. It's not remission anymore, things like this. Well, so it depends if you mean the unit. So okay, you can drop the unitary of the symmetry. So you can do, I don't know, some Li Yang example, that's fine, right? But you can also kind of drop the, so typically if you work with a non-semi-simple input, then the theory will not be able to have will not be a remission often. So then you will drop the unitarity of the theory itself. Yeah. Okay. So let me start with Vec-G symmetric models. So this is nothing really new, but I'm going to sort of package it in a specific way that makes the generalization to other symmetries easy. So the setup is, so first of all, I need to pick my lattice, which we can take to be a subset of Z. I won't worry too much about like boundary conditions. I mean, for what I'm going to say, you can assume you have an infinite lattice, or if you want open boundary conditions or even closed boundary conditions. I mean, it comes with some subtleties, but for what I'm going to say, I'm not going to address these subtleties. The Hilbert space is a tensor product space in that case, where V here, so first of all, let me introduce a basis right away for this vector space V, and it is an object in rep G. So it has a G action. I have a sister algebra of local operators, which is also a tensor product of some matrix algebras. Okay, these are, you can interpret them as bounded linear operators on the Hilbert space. And I can choose a specific type of such operator. So if I take, for instance, a G equivariant map, which is a morphism in this category. So a G equivariant map H from, let's say, 2 copies of V2. Let me just introduce a notation as well for the corresponding algebra homomorphism. Okay. So I take 2 copies here, which ultimately will give me a 2-body, like an operator that acts on 2 sides, but you could take n copies of V. It doesn't really matter. And then this operator, I can embed it in my algebra of operators by tensoring with the identity. So the idea here is that, okay, my Hilbert space is just some copies of V. They live at some sides. Here I think of these 2 copies of V as being 2 neighboring sides. I can tensor with the identity, and this gives me an operator that acts on the whole Hilbert space. And so Hamiltonian, we can construct the Hamiltonian translation invariant by just summing over the sides. Okay, so that gives me a 2-body Hamiltonian. And this Hamiltonian will be symmetric by virtue of the fact that this is a G covariant map. It's basically an intertwiner, if you prefer. I pick one. Yeah. Well, it's a choice of model. I mean, yeah, it doesn't matter. I mean, now, of course, if I want to, I don't know if you want to write down a specific model, then you will have to pick a specific edge, of course. But yeah. And so it's symmetric, and the symmetry operators, well, it's just given by the G covariant structure of your vector space. It looks like this, right? So you just take the, so again, by this, I mean the abending in the total algebra, and then I just take product over those. And so it's going to commute with the Hamiltonian again because this map is G equivariant. So V here can be anything. Typically, we will choose V to be a faithful representation, such that you have a faithful action of your symmetry. But it can be anything. But now, of course, if you have in mind, let's say, I don't know, like you want a spin 1/2 model and spin 1 model, of course, the dimension of this vector space will have to match with the kind of degrees of freedom you have in mind. But it can be anything. So in that case, my Hilbert space, indeed, I chose it to be a tensor product space in the beginning. So this is really the ordinary setup. And when we say we have a spin model that has a G symmetry, secretly, that's exactly what we mean, right? And this, you could do it, of course. So here I said it's finite, so the group is finite. But the usual spin models, like Heisenberg models, for instance, you get them like this. You pick as a given representation of SU2, and then you do this for SU2 or SO3. Okay, so now what I want to do is that I want to rewrite this in a slightly different way that will make the generalization a little bit easier. And the idea is the following. So instead of kind of drawing my Hilbert space like this, I'm going to draw it like this. So I'm going to, the lines are going to represent my copy of my vector space. And so I want to think here of the corresponding degree of freedom, which is just a vector in a vector space, as being actually a morphism in a category. So what I'm going to do is that this dashed line here, it represents a copy of the one-dimensional of the complex line, which is the unique simple object in the category of vector spaces. And in that case, I can think of this VA here as being inside, as representing a morphism in this RAM space. Well, here I'm being a bit sort of fancy for saying something completely obvious, but technically V is an object of rep G, but you have a forgetful functor where you basically forget the G action on your vector space. So then this is just a vector space. And here, then by that I mean, okay, you forget this structure, and then you just take the usual tensor product. So if you want, I can just take just the tensor product. And this is of course isomorphic to V. But I want to think of these local degrees of freedom as being maps in the category vec. So here the idea is that you can essentially this object V acts on this complex line, and then you get as many copies as C as you have the dimension of your vector space, and the basis vectors for this home space, they agree with the basis vectors of my original vector space. So I can rewrite my Hilbert space as tensor product over the sides as these guys. Okay. Okay, the reason I'm doing this, because now it gives us access to some. So of course the idea is to make use of the string diagram calculus of fusion categories. And in particular, I can rewrite the action of the symmetry line in a nice way. I'm just going to do it here. So I have a given state in this vector space, and then I can think of the symmetry operator. It should be a topological line. So here we can really make this topological line interpretation very explicit. So I have an object, a simple object in vec G, because my symmetry is vec G. And here, okay, I draw it as a line. So technically, my symmetry operator, you can write it as a tensor product. Yeah. So I'm reading the diagram here like this, from the, if you want, from bottom left to top right, if you want. Yeah. And so here, okay, so technically, since the operator is a tensor product operator, we might think, okay, it's a bit of an overkill to think of it as a line, because this is just a product of points, if you want, rather. But in general, of course, when you have a non-invertible symmetry, this is really the right way to represent it is really a line. So I'm embracing this approach right now. And so what I can do is that the same way I have an action of rep G on vec, which gives vec the structure of a module category of a rep G. I can also have an action of vec G on vec. So I have another forgetful functor here, where instead of forgetting the G action, I'm forgetting the grading. And I just retain the vector space structure. And so using it, what I can do is that I can do the following manipulation. You can sort of absorb, if you want, my line in this way. So this doesn't do anything. But here I'm introducing these new junctions, so using the action of these lines on vec. And now, in order to recover the actual operator, what I would like is that right now, this is something I'm forcing, but this is something we can derive later, is that when I move a line, so one of the line labeled by G past a line labeled by V, which is kind of some commutation relation, it should act correspondingly on the corresponding vector space by G. So this actually, what it does is that technically it endows vec with a specific bimodule structure between vec G and rep G, which happens to be an invertible one. Like here, this is something I'm sort of kind of imposing to recover the usual action. But I'm going to explain in a second how this is actually not really a choice. And so, yeah, so the idea is that, okay, you can use this relation by moving all these lines past the V line, so that then you're left with configurations that look like this, which then you can just cancel. You can just cancel these bubbles without doing anything. So every time you move this one past it, you act with G on the corresponding vector, and so you do recover this action. If that makes sense. Maybe if it doesn't, it would be a good time to ask, because otherwise the rest is going to be a bit obscure. Okay. Right, so for the Heisenberg model, so one question is, maybe you can ask, okay, do you want the whole SO3 at the symmetry of the Heisenberg model, or maybe let's just, to really fit within that framework, we could just say, okay, let's focus on the subgroup of SO3. So then, indeed, we would build, so you would choose, so let's say if I don't know if it's a spin 1/2, spin 1 Heisenberg model, you have to choose the representation accordingly, right? So typically you can take some dihedral groups that nicely, and then when you do this operation, right, this graphical calculus, at the end of the day, what we do is that we just say, okay, the symmetry acts by transforming the vectors of your vector space. We're just using basically the fact that individually these have a G action, and then we act simultaneously on all these vector spaces by the same group element. That's all what the symmetry action is. Right? Yeah. You mean this? So this is just meant to, it's a depiction of the vectors in my Hilbert space. And using this graphical calculus, I can derive the action of the symmetry lines also in a graphical way. That's the idea. Okay, but now, so here I sort of gave you the answer, but now we can ask, okay, if you're just given that setup and you want to deduce what the symmetry would be, well, the idea is the following. I'm just going to stick it somewhere here, so that is to say that, okay, this formulated like this, my vector in my vectors in my Hilbert space, they correspond to specific morphisms in the category of vector spaces. And so a symmetry, what we want is something that is going to act on this morphism. So it's going to act on the category of vector spaces. So it's going to be a functor from vec to vec, because you want to preserve, I mean, it's a symmetry, so it shouldn't change the Hilbert space. So we should still be, the degrees of freedom should still be valued in the same thing. But this action have to be compatible with the fact that here I have this action from a representation of G. It has to, if you want, it has to commute with it. And that's the structure of a rep G module functor. So this is a functor from vec to vec that is compatible with the action of rep G. And this is a computation you can do. So often we draw it, we represent it like this. And we say that this is the Morita dual of rep G with respect to vec. And this you can verify is equivalent to the category of graded vector spaces. Actually, it's equivalent to the fusion category of G-graded vector spaces, but the fusion structure is given by the composition of these maps. Yeah. Well, so here my symmetry is always the fusion category, right? I mean, here indeed, you don't gain much by promoting G to vec G. But of course, in the general case, there is no way around this, right? I mean, if I just give you a fusion category, yeah, so the direct sum, we use it in particular when you, so I'm not going to talk about this, but when you use these lines to define twisted Hilbert spaces, so then you have a vector space that is sort of labeled by the whatever you twist it by. The direct sum of the lines, if you insert like a non-simple object, which is a direct sum of object, then it's going to translate into a direct sum of twisted Hilbert spaces.
So by doing direct sum, you sort of increase the Hilbert space?
Well, it's more like, so I have the situation in mind where I have I'm working, let's say, on a cylinder. I'm introducing a twist here. And here, this is not necessarily a simple object. And let's say it's, I don't know, let's say it's a direct sum of two simple objects. It's going to translate into a direct sum of the twisted Hilbert spaces, right? You wouldn't really be able to make sense of if you didn't have this linear structure, you wouldn't really be able to make sense of a direct sum of twisted Hilbert spaces, right? At least as coming from one defect. So if I just put if I twist, so this is to define the twisted boundary condition, for instance. When you insert a twist like this, which I can do nicely in that framework as well, I can insert a twist over here. Yeah, I will do it actually later. This modifies my Hilbert space. If I keep this fixed, it's going to modify the action of this Hamiltonian here around that defect, right? And so this is, okay, this is a twisted, this is what we call a twisted Hilbert space, like twisted by the defect. If I want, now if I say, okay, I want to take a direct sum of Hilbert spaces that are twisted by different lines, and you want to think of it as coming from one line, you need to be able to consider direct sum of lines in the first place. So if you have just G, you cannot take direct sums of group elements. So this is why you need a linear structure. So, yeah. I mean, it's a bit, okay, it's a bit formal, of course, for the case of G, but as soon as we go to an actual fusion category, then, well, the tension disappears because there is no confusion possible, right? I mean, yeah. Sure. Right, some mixture of, yeah.
The old side now because you take simple object, but if you take your simple rate, if you did this with the early topic,
Sure, sure. Yeah. No, but that's not, yeah, sure. Okay, so now I want to use that setup to talk about gauging. So I want to gauge that symmetry. Well, I want to consider gauging operation or even twisted gauging operations. The twisting part, I will clarify what I mean by this. So first of all, okay, so before I maybe define what I mean by gauging in a more physical way, let me just spell out the fact that, so in general, when you have a fusion category, we know what classifies the different gauging operations we can do. And these are given by so-called, so delta separable symmetric Frobenius algebra in my fusion category, which in that case is vec G, but this is true for an arbitrary fusion category. So I'll put this in brackets because, so we do sort of make use of this additional structure, but this is not really something that we choose. It's especially clear in that example, that if you choose an algebra that is nice enough in a fusion category, which is something that is very nice, then you can get sort of for free all this additional structure. I just want to emphasize that this is not really something that we choose on top of choosing an algebra. It's more something that we get for free once we chose an algebra. So what is an algebra? an algebra is given by, so it's an object in the category. It has a multiplication, which is a map in the category, and also a unit. Okay. I won't talk about, I will just exemplify what these adjectives mean in a specific context, but for now, I won't describe it. So in the case of VecG, these were classified, the indecomposable algebras, they were classified in particular by Ostrich. And this indecomposable algebra, they are labeled by a choice of subgroup. So it's a pair, it's a choice of subgroup, and a choice of cohomology class of that subgroup, second cohomology class. Okay, so this subgroup part, this is just, so again, I'm going to explain in a second what I mean by gauging, but this is the familiar notion that we don't have to gauge the whole symmetry, we can gauge just a subgroup of the symmetry. And the choice of cohomology class, this will be the twisted part. So what are these algebras in general? So I gave you the classification, but okay, in general, an algebra in VecG, what it is just an algebra, which is also a graded vector space. So given this data, how do you construct this? So the corresponding algebra is just a twisted group algebra. So let me introduce a basis for this. And let me just write down what it means. So it's twisted by the two cocycle. So the multiplication, so it's given by the multiplication of the group. But in addition, you pick up these two cocycle. Okay. So as an algebra, this is this. And of course, because H is a subgroup of G, it also has a G grading structure. And so as an object in VecG, I will write it down like this, just to kind of to remember that it has the additional G grading structure. Okay, so what do I mean now by gauging? So gauging, what it is, the idea of making the symmetry local, right? What we would like to have is that we will have a theory that is, so it's not going to be the initial theory, it's going to be a new theory, which is invariant when you act locally with your symmetry. So in the case of VecG symmetry, where the operator is just a tensor product operator, it's fairly easy to even just define what we mean by local action. Is that you say, okay, you just act on one side, and somehow we would like the theory to be invariant under this action on one side. But let's kind of anticipate a little bit. In the case where you don't necessarily, you have a non-invertible symmetry where the corresponding operator will not be a tensor product operator. Even before we try to make this to be invariant under this local action, we have to define what do we even mean by local action. So why isn't it completely obvious? Because if I use my graphical calculus here, by local action, what we would like to do is that we would like to say, well, I would like to consider sort of just like a piece of my symmetry line, just act with this piece on this vector space and ask, okay, well, now what do I need to do in order for the theory to be invariant under such a local action? So you can't do that. So this would, because doing that would imply that there would be a junction here. So this would imply that there will be a junction in, so VecG. So let's say this one is labeled by CG, from CG to C. But since the maps have to preserve the grading, so the trivial line would be the one labeled by the identity. Since if G is non-trivial, then this is 0, right? So you can't actually just terminate a line like this. So we can't just naively define the local action of G. What we have to do is we're gonna need to introduce these defects I drew there, and we're going to introduce defects that are labeled by our choice of algebra. So we do the following: between every two sites, we insert these additional lines. So this T carry V and this carry now this object, which is not a simple object, of course, in general, everywhere. Okay, and now that I have this twist, so first of all, when I just do this, it means I'm extending my Hilbert space, because in addition to V, now I have also a copy of this algebra of the underlying vector space at least. So I have a much bigger Hilbert space. But this additional twist now allow me to actually define this local action, because now I can actually terminate my line on this twist, right? This makes sense using my graphical calculus. I can actually do this. And it makes sense to define the action of a line, let's say, Cx. So here, let me just, so remember that here you have a vector in V, here you have a vector in this graded vector space. And you can define the local action. So how does it look like, this local action? Let me zoom in. So what we are using essentially is that if I have, so this is where actually I'm secretly using the fact that I have, so in particular, I have a separable algebra, which means that I can split the multiplication, what it means basically is that I can sort of reverse the arrows and define a junction with opposite arrows. So here if I have Cx, here I'm gonna have Chi. The multiplication, so I'm just multiplying the corresponding group element, but this multiplication takes place, so I'm using the morphism that is compatible with the multiplication rule of this algebra. So here I'm picking up a twist, a co-cycle as I'm doing this. And here if I have this one, okay, here I get a different co-cycle. So I'm just using, so as I said here, this is the multiplication of my algebra. Here I'm using the corresponding co-multiplication, and which is so twisted by the co-cycle. So there is a bit of convention involved to actually read out the proper co-cycles, but this is just what you're getting. You can actually build a project. So now what we want is that we want to define a theory that is so invariant under such a local action. So what you can do is that you can actually just build a projector, which I would call maybe a Gauss projector, to enforce the corresponding Gauss constraint, to enforce the invariance under this local action. And what you do is that you just put your algebra everywhere. Okay, every line is labeled by the algebra, and so on. And so what it's going to do is that here you're going to sum over this line x. You're going to do basically a group averaging. So you sum over all possible x, and you enforce the fact by doing the averaging, you enforce the fact that then it's invariant under performing such a local action. So you can always kind of brute force this by just taking any state and acting with the projectors. What we would like to do rather in this context, by gauging, we often want to sort of identify an effective Hilbert space, so effective degrees of freedom that immediately solve the Gauss constraints. So here we have an extended Hilbert space, we have more degrees of freedom, but then we have these constraints. So we want the theory to be invariant under these local actions. And so you can ask, can we actually solve these constraints, or as many constraints as possible, to kind of simplify the theory and derive an effective description. So what we want really, the Gauss laws here, is asking for an invariance. Invariance under the following transformation. So I have a degree of freedom in my algebra. Here I have a vector in my vector space. And so I'm just reading out what this diagram means. It transforms in the following way. So the action of a local, so it's like the twisted local action of this line. So you could just ignore the psi and then you would just do a regular gauging, but I'm including the psi to do the twisted case. This is what we get. Okay, so this is the action locally, right? And we're asking for invariance under this action. So there is so I'm gonna skip a few steps, but how can we derive an effective description that immediately solves for this constraint, the degrees of freedom that are manifestly invariant under such a local action? So these degrees of freedom, they transform projectively when we act with H. because actually it's literally it's like the regular projective representation, and you can think of this twisted group algebra as the regular projective representation, which decompose into irreducible projective representation. So these degrees of freedom transform projectively. This one transforms linearly, and this one transforms projectively again. And so we're asking for essentially states that are invariant under such an action. What we mean is that we're asking for states that depend essentially on some vectors that live in the invariant subspace of this tensor product. So let me give the solution, and then maybe I can clarify what it means. So we end up with an effective Hilbert space, spanned by vectors. But we still have V over here. But now I'm replacing the choice. Instead of having the category vec here, it's going to be something else. It's going to be a choice of projective representation. So the category is going to be the category of projective representations. So I can choose on all these lines here, I can choose a different projective representation. And now I'm picking a vector here, or whatever, alpha I, which lives in this Ram space. So here where I'm using the fact that, so the reason I'm using this graphical calculus is because I have an action of rep G on this category of projective representation. So this is this guy over here. The action is given by restricting to the subgroup and then just taking the tensor product. So what happened, as I said, these degrees of freedom transform projectively, so I can kind of decompose into irreducible projective representation, and then asking for the invariance means only depending on something that is in the invariant subspace of the tensor product of these things. So I'm acting with V, so this tensor product, this is these three tensor products, and I'm asking for degrees of freedom that lives in these invariant subspaces. So the effective, if I write it more symbolically, this effective Hilbert space is the following one. So it's not a tensor product space anymore. That's given like this.
Sorry, a basic question, but could you go again? What is the relationship between the two diagrams, like the shape with the ladder? Yeah.
There.
This one and the Gauss projector one.
So in a way, this is like I wrote it in components. It's like this guy as an object, it decomposes like this. So these are the simple objects. It decomposes like this. And now, so you can decompose all of them, and then you can ask for each component, how do they actually, so you cannot label everything you want. It has to respect the morphisms that you chose. And in particular, it has to be compatible with the multiplication rule. So essentially, once you're a bit careful with the orientation, it's just saying that you take the product of the corresponding group elements. It has to be the identity around every junction.
Would it be correct to say that the right-hand side diagram is a direct sum over the left-hand side?
Yeah, I mean, if I take direct sums over everything, and in particular over this one, then yes, it would give you. Okay, so we arrived at, so this is our effective description. So now where we have our degrees of freedom technically are morphisms in the category of projective representation of H. That's the result of doing the twisted gauging of the vec-G symmetry. Of course, when you specialize to a certain group, if you choose maybe the group to be abelian, these things can simplify further, but in general, this is what we can do. Okay, so now the question we want to ask is, so we have a new theory that has new degrees of freedom, and we want to ask, what is the symmetry of this new theory? Because actually the symmetry changed in the process, so we know that by gauging the symmetry, we are getting rid of some symmetry operators, but we are also gaining new ones. So something I forgot to mention is the reason we can't do that in the first place, the reason we, well, I gave you the solution, but the reason we were able to derive this effective description in the first place, which means like solving for basically all the Gauss laws, is because the corresponding projectors, thanks to the Frobenius structures, they are actually local commuting projector Hamiltonians. So you can actually find states that satisfy simultaneously all of them, which is why we were able to arrive to such an effective description. So this is where the Frobenius structure kicks in. Okay, so what is the dual symmetry? So the dual symmetry, well, here I'm going to use the same approach I had earlier, which I erased, but it's saying that, okay, we have degrees of freedom labeled by morphisms in rep psi g. So symmetry is something that should act on this. It should be a, well, it should be a functor from rep psi h to itself. And again, it should be compatible with the rep g action, which comes from the fact that we still have our original degrees of freedom here in rep g that acts on these degrees of freedom. And so this is, again, and this is what we call the Morita dual of rep g with respect to rep psi h. Where, by the way, rep psi h here, it's not a coincidence. Rep psi h is a category of, maybe it's easier to think like this, is a category of modules over the twisted group algebra. And it's actually a general mechanism which applies also when you have a category of modules over Hopf algebra. You can actually take an algebra in the category of comodules, and then when you take module over it, you get a module over the category of modules over the Hopf algebra. If you want, there is a different way of writing this. We can turn it around because our symmetry was initially the vec G symmetry. So you might want to think of this new symmetry as kind of being defined in terms of the original one. And so you can also get this as a dual of vec G over with respect to a different, so a module category of a vec G, which I'm not going to define, but I will just tell you that you can get this module category by taking modules in vec G of the algebra that we define. And so here it's crucial to notice the difference. Like here, when I just write module, I'm taking modules in vec, which gives me a module category over rep G. If I take modules in vec G, I'm getting a module category over vec G. So that's sort of, we started from a vec G symmetry, and now we have a dual symmetry, which is given by this dual. Okay, so in particular, if we do, let me just maybe do an example. If I choose H to be G, and actually psi to be anything, it doesn't matter, then the dual is always equivalent to rep G, which is saying that when you gauge the whole symmetry, then you have a dual symmetry, which is given by a non-invertible symmetry, where the operators are labeled by rep G. What is nice with this framework is that we can also get directly not just operators, right? And yeah. So okay, here I'm giving you the kind of what encodes the operators. Now, if you want to see the action of these operators on the Hilbert space, you do similarly to what we did before. You kind of draw a line that is labeled by an object in there, and the data of this computation will tell you how to move the lines past the ones labeled by rep G, and therefore it will give you the action of this dual symmetry. I will do an example. I will do this example in a second. Let me just also say that we can, in a very similar way, we can also get duality operators, which we might want to instead, like, so this procedure of effectively what we did, and once everything is done, is that we just changed what labeled these horizontal lines. Instead of having labels given in vec, which then now it's given in a different module category of rep G. But now you could ask for maybe an operator that does that acts on the original Hilbert space, and that gives you the new Hilbert space, and that maps the Hamiltonian and everything. And you get this duality operator from the data of again a module functor, but this time, sorry. No, it's not an endo functor anymore. It's going to be a map from the initial choice of module category to the new one. And so again, from that data, you can do exactly the same way. You can draw a line, but now it's not a symmetry line anymore. It's a duality line, and then you act on the Hilbert space exactly in the same way, and it gives you the operator that transmute the corresponding theories. Any questions? Okay, let me do a quick example. So let's do the RepG symmetric case. The RepG symmetric models. So there are several ways of getting symmetric models. I could just use the formalism. So as I said, if you start from a theory that has a VecG symmetry, and if you gauge the whole symmetry, you're going to get a new model that has a RepG symmetry. But this is going to be defined on a Hilbert space that is not a tensor product space. Even though RepG is non-invertible, we can actually define its action on a tensor product space, which I'm going to do now. So it's just a different realization of the same symmetry, which to illustrate a little bit how this works when you have a non-invertible one. Yeah, yeah. Right, so here I'm being a bit quick. The reason I'm using the word duality here is that, so from the data, from this, essentially what you get is something that indeed transmute one Hamiltonian into the other, okay, which wouldn't be in duality really on its own. The reason I'm saying duality is because, so invoking, so basically what happens that duality suggests some kind of unitary mapping. And these duality operators in general are not unitary in the sense that they always project onto some sectors. So they project onto some, let's say, a singlet sector of your symmetry. So as such, it cannot be a unitary mapping. But if you include all possible twists, so if you look at all possible insertions of twists, so you consider then, and you make this twist dynamical, so it's like you add a new degree of freedom in your theory, which accounts for all possible twists. You can look at the action of this operator on this twist Hilbert space, which will map it to a twist Hilbert space with like different patterns of twists. And on this extended total Hilbert space, it is going to be a unitary. At the end of the day, what's going on is that essentially we are realizing on the lattice the fact that this being Morita equivalent, we are essentially realizing, so this mapping of sectors I just talked about is basically this equivalence is realized by this equivalence. And what we do is that when we include these twisted sectors, we are essentially realizing on the lattice this equivalence. And at which point it becomes a unitary on this kind of enhanced Hilbert space. Yeah. So this is what we justify using duality in that case. But I would say it's only a duality once you include all the twisted sectors. Yeah.
Well, put it in short, it's that what you're saying is that this functor provide a
So, but not just this one. It's like you have to realize you get basically, you have to intertwine between, I mean, you need to, so my duality operator needs to be also mapped, so you get like this tube algebra, right? Because you need to include also the mapping of the twist. So this data would only give you kind of this line over here, and you need additional data to understand how to decorate it with the twists. Okay, so as I said, let's just realize a RepG symmetric model on the tensor product space. And I'm going to do it by turning around the previous construction. So I'm going to take my Hilbert space now to be still a tensor product space of V, but now this one, V is a graded vector space. I'm kind of swapping the role of VecG and RepG. And so, for instance, it's just convenient to just take the one given by the group algebra. So we decompose into simple objects like this. Okay, we can define the algebra as before. Now the Hamiltonian, so I have to be, the Hamiltonian is going to be given by no longer a G covariant map because this is not the right structure, but a G grading preserving linear map. You get your Hamiltonian like this. And now, in the Hilbert space, so if I draw it in a way that is similar to before, it will look like this. So I'm going to use, let's specialize to this example. It's the same as before. This represents C, the unique object in VEC. And now I'm using, as before, the forgetful functor. So I'm ignoring the grading and I'm just taking the tensor product. So these basis elements here are now labeled by group elements in G. Okay. Now the symmetry, so again, the symmetry is going to be given by so-called Morita dual of VecG with respect to VEC, which in that case is RepG. So this is in the spirit of this being a kind of a duality relation. If you take twice the dual, you go back to itself. From this, you can infer that since the dual of RepG with respect to VEC is VecG, if you take the dual of VecG with respect to VEC, you should get RepG. And how does the lines act? So now I have a line. So this is really a line now because it's not going to be a tensor product operator labeled by an object in RepG. We use some graphical calculus where so now this is not one-dimensional. So it does not just, there is not a unique choice of basis vectors here. You have to kind of sum. It's basically we insert a resolution of the identity. Okay, so I'm summing implicitly over I and J here. And then I want, as before, to move these lines past the previous ones. And I'm going to use it's exactly the same diagram as before. And remember that when you move like a G line past a line labeled by representation, you act on the corresponding degree of freedom. And so bringing everything together, you end up with an operator that looks like this. So let me assume closed boundary condition, periodic boundary conditions to simplify. You end up with an operator that has the following form. And okay, throwing in some bracket notations as well. So it's an operator that acts diagonally. So my degrees of freedom here, they are labeled by group elements. So this is, here I'm sort of identifying this. So it acts diagonally. It does not actually, if you want, transform these degrees of freedom, but it multiplies by a prefactor. This prefactor is obtained by multiplying all the representation matrices and then taking the trace. Because every time here I'm summing over this I and J. Every time I go past, I'm going to have to act on the corresponding degree of freedom. So I'm going to pick up a rho G, and then you multiply them because you sum over the corresponding indices. And finally, if you have closed boundary conditions, you're going to take the trace. So that's, of course, unless the group is abelian, but otherwise, this is clearly not a tensor product operator. And this is how, for instance, so again, this is the action of RepG on this very specific Hilbert space. We had another Hilbert space before that also had a RepG symmetry, but then it acts a little bit differently. So we have many ways. So you have basically for each Morita representative, you get a different realization of a given symmetry. And so the final thing we could do with this is that we could do also, again, twisted gauging, which would require picking some algebra, but this time in RepG. And this, so not surprisingly, because since we can go from like VG to RepG by dualities, the corresponding twisted gauging should also be in one-to-one correspondence, and they're going to be labeled by exactly the same information, so a subgroup and a truss of cocycle. It's a bit more complicated to build the algebra in that case, but I'm just going to give you the formula. The corresponding algebras are obtained by taking some induced algebra. So you pick a projective representation U is a projective representation of your subgroup. You look at the algebra of endomorphisms, and then you induce it in G, and that gives you the corresponding algebra in A. And you could do the procedure we did before, but it's a bit more cumbersome in this case. Okay, I think I will just add one quick thing and don't want to keep you too long. Okay, so something that is we can also study, that is interesting to study, is that we can build nice representatives of gapped phases for this for theories that have a symmetry given by a fusion category. And so what it means like, let's go back to the case of VG symmetric theories. I'm going to ask for the classification of gap phases. If I accept the idea that gap phases in the low energy limit are described effectively by some TQFT, then this is the same as essentially asking for the classification of VG symmetric. I'm going to add unitary here, 2D TQFTs, which unsurprisingly are classified again by the same data as before. So really it's classified by, again, a choice of subgroup and cohomology class, which also labeled classifies the indecomposable module categories over VecG. And since we have a VecG symmetry, I'm going to classify it like this. So we cover the same data. And actually, the reason why this is not completely surprising is because the Gauss projectors, which I said were like local commuting projector Hamiltonians, if you think of them as, instead of like kind of enforcing the Gauss laws kinematically, if you enforce them dynamically, so you just build the Hamiltonian from these Gauss operators, you get actually a fixed point model you get a representative fixed point for the corresponding gap phases. And so what is the interpretation of this data? So we have, if for a given choice of H and psi, what I have is that I have spontaneous breaking. It's a gap phase where the symmetry is spontaneously broken, such that the set of ground state or vacua is given by the cosets. So that's just the usual story. And the twisted part, this is the statement that each ground state, which preserves some H symmetry, you have several ways of preserving that H symmetry. And so physically, we often talk about the edge modes that transform projectively. And a slightly different way of saying that is that each ground state preserves an algebra of lines that is mo eta equivalent. There is mo eta to the algebra in VecG I constructed above. So remember that this algebra is basically essentially the H, so it preserves the H symmetry, but then when you fuse lines, it's you pick up these cocycles, which is equivalent to saying that the at least from this, you can recover the fact that the edge modes of the corresponding states here transform projectively, the projective part coming from the choice of a non-trivial cocycle. Okay, the thing that is interesting is that that's kind of in the usual story. When you break an invertible symmetry such as VecG, all the ground states basically look pretty much the same. It doesn't really matter which one you take. So technically, they are labeled by a coset, which means that the symmetry they preserve is not strictly speaking the same group H. They preserve like conjugates of the group H, so they don't strictly preserve the same state, but it's obviously, yeah, it's a very mild difference. But so it's interesting to look at the difference with the RepG symmetry case. So if you look at rep G symmetric gap phase, so we're going to have exactly the same classification. But now I'm going to think of, so it's still labeled by, again, a choice of subgroup and cocycle, but I rather want to think of them as being labeled by the indecomposable module categories over rep G, which are these categories of projective representations. And also, let me mention one more thing that is often here in the invertible case, we say that the symmetry is broken down to H, thinking of H as a kind of a subsymmetry, which indeed technically it is a subsymmetry of the initial system where you have a subfusion category. But this is actually very specific to the invertible case. And in particular, already I'm going to show it here, when you have a non-invertible symmetry, you can't say that the symmetry is broken down to a subsymmetry. And it's actually, in general, it's going to be broken down to actually an algebra, which is why I'm phrasing the usual classification of gap phases in that language. So we have spontaneous breaking. Such that the set of ground states is given by the irreducible projective representation of H. Well, it means that your vacua are labeled by an irreducible projective representation. Okay. And so in particular, what it means that if I take, so let's say I have a representation G, okay, I have a symmetry operator labeled by G, and I act on this on a ground state labeled by U, where U is a choice of irreducible projective representation. So how does the symmetry act on it? It's just going to act essentially by, by tensor product via the restriction. So let me explicitly. Okay. But what is interesting is that depending on your group, so usually we're used to the case, like let's suppose that H is G. So we're supposed to break the whole symmetry. We're used to the idea that if you act with any symmetry operators here, if I break the whole symmetry, I act with any G on a state, I'm acting basically by multiplication, then I'm obviously getting another ground state. I'm always getting an orthogonal ground state. But here, it is possible that if U is, for instance, a higher dimensional representation of rep G, it is possible that if I choose V, for instance, to be a one-dimensional one, this tensor product, so in some cases, we actually return just U, right? So it's possible. It's possible that this happens. So what it means that even if you break some even the symmetry is broken, you have certain ground states. So first of all, the ground states are not all on equal footing, as you can predict from the fact that all the representations don't necessarily have the same dimension. If you have a higher dimensional one, it is possible that this line is actually left invariant by some symmetry. And if you sort of look at all the lines that are preserved in such a way, in general, you realize that they don't form a fusion subcategory. So this is why you cannot say that the symmetry is broken down to a fusion subcategory. But what you can say is exactly the analog of this one, is then you can say that each ground state preserves so an algebra that is more eta to this one. So that's the notation I used. Well, I didn't use it, but this is I define it like this. And in particular, you see that in order to define this algebra, I have to make a specific choice of projective representation, which is exactly the same as the choice of projective representation here. So the statement is that actually each ground state, when you have a non-invertible symmetry, they will be protected by different symmetry lines. But all these algebras have to be Morita equivalent because you should always be able, it shouldn't matter which ground state you look like. Like for instance, you want to study a phase transitions between two gap phases protected by some non-invertible symmetry. Maybe you have an order parameter. It shouldn't matter which ground state you consider. You should be able to identify the phase transition in the same way. But since they behave, at least naively, very differently, it's not completely obvious this is the case, but it's going to be guaranteed by the fact that they preserves, the symmetry they preserve, if you want, is encoded into an algebra in the category, and they all have to be Morita equivalent for like consistency. And I think I will stop here.
Any questions? Yeah.
The
Yeah.
last story that you told me that they have to be Morita equivalent to A, is this like a physical, we want this to happen, therefore we impose it, or does it follow?
So the idea is that ultimately the gap space is labeled by the choice of module category. You can get these module categories by taking modules over algebras. As long as the algebras are Morita equivalent, you get the same module category. So here, this is in the spirit that from any ground state, I should be able to reconstruct which gap phase I'm in. This is what I was saying, like if you try to study some transition and you look at expectation values of some order parameters, it shouldn't matter which state you consider. So you should be able, this is what I mean, you should be able to reconstruct which gap phase you're in and therefore the module category from any of them. And this requires then that they preserve like Morita equivalent algebras. Otherwise, you could end up with, well, yeah, you wouldn't end up with the right conclusion. I mean, okay, of course I'm skipping a few steps here, but that's morally the idea.
That just follows from the formalism as well.
Yeah, so from the formalism, of course, if you know already what you're looking for, then yes, it's really by construction. Like here I can show. So what's happening actually is that these algebras, you get them as something that is called the internal home. So from any object in the module category, you can reconstruct the algebra. So this is secretly what we are using here. So this is actually the internal home associated with U. So yeah. Yeah.
So this formalism, I'm guessing that this applies to bosonic lattice models.
Yeah, I mean, okay, so okay, with some stretch of formalism, you can try to generalize to fermions. Just the mathematical framework is not the right one. You will need to go to, well, like superfusion categories, or what you can do also is that you can sort of phrase Jordan-Wigner in this language. So you do start from something that is a fusion category, but then you would take a kind of a super module category, and then the dual of these would give you something fermionic, for instance. So this is how you would get Jordan-Wigner, for instance. But yeah, it's under control in the bosonic case. It's speculative in the fermionic case. Yeah.
Does it work for non-symmetrical half algebra? You mentioned that it works.
Yeah. No, it works. Yeah, it works. It's just that so then you have some features that are, well, interesting, but also maybe not very desirable from a physics point of view. So if you have a non-semi-simple tensor category, you can have like continuums of module categories, so parameterized by a real number or something, which is fine. But then, for instance, if then you want to kind of classify gap phases by module categories, that's not okay anymore. Because then if you have things that are connected by a real parameter, they should all be in the same gap phase. So then we would need to, yeah. So what the idea in that case is, yeah, is that all these module categories that are sort of part of the same path would correspond to the same gap phase, probably. I mean,
So in
yeah.
particular, when you wanted to gradient, you wrote this effective
Mhm.
space, and then you use a tensor product over module categories, but then that doesn't work for non-semi-simple one, right? At the end, down there, you wrote something like
There?
effective.
Oh, you mean so if you have like project, if you, yeah, so then you no, but you can, you have to be more, yeah, you have to redefine things a little bit. But you can, we can deal with projective objects that are not simple. They have actually a nice interpretation in that context. For instance, what happened is that if you have so you can have like here, for instance, two ground states that are labeled by a simple object or its projective cover. So they have a map between the two. So these give you two distinct ground states. But then the interpretation is that in the IR, in the infrared limit, they would correspond to the same vacuum. We should actually make a distinction. This forces us to make a distinction between kind of ground states and vacua, because all the things that are projective over each other, they should ultimately converge to the same vacua. And this is something you can see there using kind of an operator algebraic formalism, where it's well known that there are certain states that are actually orthogonal, but we know that they actually give you in the infinite volume limit, they actually converge to the same one. So this is a mathematical version of that.